Hello all. So let's continue with our problem number 98, which is validate binary search tree. So what's the definition of binary search tree? So it's simple. It's written here as well that and all the elements on the left half of the root node. So here the root node is 2. So all the elements on the left half should be strictly less than 2. Okay. Mind me, strictly less than 2. And on the right half should be strictly greater than. It should not be equal as well. So here it's just a single element, but what we have a entire tree on the left half. Like here it's also single element, but on the right side you can see it's a tree. So we can say it's a subtree. So here that's when the definition is written that an entire left subtree, okay, of node contains only nodes with keys less than the node's key. So this is the node, then left subtree should be less than, okay, the current node. So this is also called root. So I'll address this as a root as well sometime. And also similarly on the right, okay, then you can see that it should be greater than. So here you can see on the right it's greater and on the left it's smaller. That's why the output is 2. But here it's not the case. Left half is smaller. You can see 1 is less than 5. But on the right here you can see that it's 4. It's not greater than 5. So here it's the explanation as well that it's less. Now you might wonder how this input is given. Like this is an array or what? No, so it's not an array. You can see it's a root. Okay, it's a tree node. Okay, a root of type tree node. And here they have given the definition of binary tree node that what it has. It's simply it has some value. So let's say this is my node. Then what its value? Its value is 2. Its left side and its right side. So its left side is 1 and its right side is 3. So if someone tells me the root 2, then if I write root dot left, then I'll get the 1. And if someone tells root dot right, then I'll get 3. Okay. If I am at this is my root node, then if I write root dot left, then it's nothing. So I'll get none. And also similarly, I'll get none for root dot right. So things will be clear, but the goal is to study recursion with this problem. So let's like go to the whiteboard. So now I forgot to explain you that how this is written. So how this is written, all the elements on the first level, so it's just 2, then all the elements on the second level, starting from left side. So 1 and 3. Similarly here you can see we will start from the root, all the elements on the first level, just 5. Then here you can see it's 1 and 4. So I'll write 1 and 4. Now I'll again come back here on the third level. Okay, this is first, this is second, this is third. And you can see there is nothing. So it's both are null for 1. You can see that there should be 2 elements, but it's nothing. So we can consider it as null. So on the very last level, we have first 2 elements as null, and then comes 3 and 6. So I hope this is clear. I mean, I don't think it was that necessary, but it's good to know that how they are writing the root. This is not an array. If you mismatch this with an array, it is not fair. So let's focus on solving this problem, but using recursion. There are other approaches as well, but our focus will be recursion because recursion is really important topic to understand. So I'm taking a binary tree again, but this time it will be a bit bigger as compared to the cases which are given to us. A bigger binary tree. So let's say I'm randomly writing. It's starting with 100. So we know that left half should be less than 100. So let's set 50. I'm just randomly writing, and let's say 150. Then what we have to do? We have to go down here and here as well. So what we will do? This should be less than 50. So what we can write? Let's say 25. And this should be greater than 50, but it should not exceed 100 because our root node is 100. And we know that on the left half, all the values should be less than 100 strictly. So let's write 75. It's not like I'm writing just exact midpoint like 25, 50, 75. These are just random numbers. Okay. So similarly, let's write here, let's say 120. It should be greater than 100. Okay, but less than 150. And similarly, we should write something greater than 150. So let's write 180. Okay. So let's consider one more level as well. to make things more complex. I mean, it won't be complex, it will be just more time consuming for me to explain. I think it's the very first problem and it's worth a time. Okay, so on the left half it should be less than 25, so let's write 10, and on the right half it should be greater than 25, but it should not exceed 50, because we know that everything lies on the left half of 50. So let's write 30. Randomly I'm writing. Then here it's getting a bit a mess, but I hope it will be fine. uh, Left half should be less than 75 but should be greater than 50, so let's write 60. And right half should be greater than 75 but should not exceed 100, so let's write 80. Similarly, left half should be less than 120 but should be greater than 100, so 110. And here should be greater than 120 but less than 150, so 130. Random writing. Less than 180 and but greater than 150, so let's have 160. And here let's have 200. Doesn't matter. Okay, so this is a simple binary search tree. Mind you, this is a binary search tree. There's a difference between binary tree and binary search tree. I'll It's a really simple thing, but I'll let you figure out that. So let's continue. Now we know that the definition now, that our left subtree should be greater than right subtree. Or right? All Sorry, left subtree should be less than sorry, what I said. Our left subtree's values of all the nodes should be less than the root node, and on the right side of that root node, whatever tree exists, entire subtree, all the values of that nodes, or all the values should be greater than the root node value. Okay, that's the definition. So how we will figure out what to do? So we know that I will start from here. Now you will say, why you came all the way down? We can't come all the way down, right? We have to come like this, from 100 to 150, then way on the left, then way on the left. Why? Because we know that if we write this, that it should be not in it should be in increasing order, or you can say non-decreasing order. That firstly it's 10, then it should be 25, this node, and it should be 30. Whenever if it's not in the non-decreasing order, okay, then it's a breach. It should always be in the non-decreasing order. So what we did is, because we have to check that this is less than 25, and then 25, this should be less than 30, then we go all the way here to 50. So then comes 50. This might be tricky for initial like for the first time viewers. So just what I'm doing is I'm just checking I'm just writing the numbers, okay, in ascending order. You can say that. And if there is ascending order is not it's not followed anywhere, we can directly say that the tree is not a binary search tree. That's the only logic. Okay, and we know this is a logic by the definition. So there is some pattern that you will notice. Let me just finish writing all the nodes. Then after 50 it should be 60. Okay, so I'm writing 60. Then it should be 75. I'm writing 75. And then it should be 80. I'm writing 80. So after 80 we should go all the way on the top to 100, right? You can see. Now you might notice something, but if not, let me just finish. After 100 we should come all the way to down 100, 110, and then 120, and then 130, 120, 130. Then we should go to 150. Then again come all the way down 160, then 180, and then 200. So it should be 160, 180, and 200. So I don't know if you find the pattern, but the pattern is something like this, that if I have given a simple binary search tree like this, that very simple, this is also in our test case, we know that this is a binary search tree because left half is 1 smaller than 2, right side is 3 greater than 2. It's a binary search tree. So what we have to do, we have to just check this 1, 2, and 3, this should be in the ascending order, or you can say non-decreasing order. So how we started? We started from 1 and then went to 2 and then came to 3. So it was something like this: 1, 2, and 3. We started from here, went to the middle, and then went to right. So it's always like we go to the left, then go to the middle, which we call it root, and then go to the right side. Correct? So the same thing we did here, it's just the bigger binary tree, that's it. So what we did, we went all the way on the left side until we are hitting the very last one. And then after 10, we went to 25 and then 30. So it was like this: left, root, and then right. Correct? Left, then root, and then right. And after this is being finished, we went to 50. You can see after 10, 25, and 30, we have hit the 50. Why? Because now let's consider this everything, this entire subtree as single node. So this was the left side. This is done. So what we will do? We will go to root and then we will go to its right side. So again, right side, it's not a single node, it's a tree. So again, we will go to its bottom, that is 60, then 75, and then 80. Correct? And now we are done with entire left side. You can see. So then we will go to 100, and that's why after 80, I wrote 100. I hope this makes sense. And after 100 is done, we are now on the right half. Okay, this is the right half. So again, what we will go all the way back to the left side, because firstly we are going on the left. So that's why after 100 it's 110. And now we will continue 110, left, middle, and right. Left, root, right. Okay, now the left half is done. So I'll go to here, which is 150. So I have written 150. And then I'll go to the right half of this 150. And we know that we have to come to the all the way to left side. So after 150 it should be 160, then come to the root and then right. So in short, this left, root, and right is being followed. And such a traversal of a binary search tree is called in order traversal. Why in order? Because root is inside left and right. That's why it's called in order. Similarly, we have pre-order as well. I think with the name, it's easy to guess. So in pre-order, root should be first and then left and right. We will see this as well, and we will solve other problems that when this will be used. Similarly, we have post-order traversal, in which we have root at the end and we have left and right. I mean, and also left and right position doesn't matter. You can write right, left, it doesn't matter. Only matter is root. That if we are processing root at the end, then it's post. If we are processing root at the beginning, it's pre, and in the middle, it's in order. So here we will use in order traversal. I hope this is clear that why we are going to use in order, because we have to have the left side should be less than the middle, and then right side should be greater than the middle. So the pattern itself suggests us to go with the in order traversal. So I hope things are clear. Now let's move to the recursion part. And for that, I have to make this binary tree again. So here is my binary tree again. And now we will understand the flow of recursion step by step. So we know that we have to write an in order traversal function. So let me write the definition of that function. It's just define, and we will write in order traversal, in order function. And since it's a definition of existing class solution from the Leetcode, so I'm just passing the self, but I mean, it doesn't matter here. So let's just not write that. That's the definition, and we are passing the root. And this is of type tree node. It's not the value. Okay, so let me write the type of it, that it's of the type tree node, and we are returning nothing. It's just we are doing a recursion. We are not returning anything. So return type should be none. And we have the function. Now we know that we have to go to the left part first, then right part, and then root. sorry, left part, then root, and then right part. Okay, so if I'll draw this again, so let me have 2, 1 and 3, the simplest case. What we have to do, we have to go to the left. If we start from here, we have to go to the left first, then come to this position, and then go to the right part. Okay, so left, root, right. That's what we have to do. So let me tell you how to write recursion first. Okay, so any recursion based function has two cases. One is called the base case. So first will be the base case, and the other will be the logic case. Now, but while writing the function, we will write logic case first and then come to the base case. So we know that what's our logic case? Logic case is we have to call our function again. So it's like self dot in order function again, but we have to call for first for the left side. Then we have to process our root. Okay, so I'm here for processing. I'm just writing print root dot val. Okay, and I'm just writing is up. Just it will be clear why I'm writing this. And then left is done, root is done, and then we'll come to the right. So it will be in order, and I'm writing root dot right. And again, for just explanation purpose, I'm writing print the root dot val, the value of the root here, and here I will write is down. So what is up and down is means is that root is up and it's not yet done. And when we hit the down for that the same root, we will say it's done. Okay, so when up and down both is done, then both left and right of that particular root is done. That it will be clear when why I write is up is down. But let's focus on the base case now. What can be the base case? So the base case can be that if my root is null, or in Python we write none, in Java it's null, then we just simply return nothing, but it's just because it's a none type return. So we'll just return to the place from where the function is being called. Okay, so why I wrote this when root is none, just return, because we know that until when we have to go to the left side. It's not like we have to infinitely go to the left side, right? Here for this node 1, the left side is none and the right side is none. Similarly, this is none and none for 3. So that's why when we hit the null, we have to go back. So we are done with this node. If we hit the null, okay, so then we have to go back. And that's why I have written this as the base case, that if we hit the null, we are done, okay, with that node. It will be clear how we are done and how we are not done. So let's start. So always in recursion, we have a stack. This will be over the I mean, just this is just for the explanation purpose, but this will be in the memory. You can't see this. What's the stack? But stack is always maintained to store the function which are being running, right? Because it's like function calling itself, then itself and itself. So it will be like recursive calling. So we have to store that. How it will be stored, we'll see that. And here I'm writing this print statement. Okay, that is up, is down. All these things I will be writing here. All the prints. Okay, so let's continue from the very base. That let's do for this as of now, so that it's clear and easy. We start with 2. So firstly we'll check 2 is the node, as I said. So it's not like value 2, it's 2 is the node. So we'll check is root none? No. Then we'll go to the logic case. And again we hit the same function, which is this one. So now what we will do, firstly what happens is we were firstly executing in order of 2. So 2 will be put inside the stack, because while executing 2 we hit again the same function. So the function that was running is still incomplete. So that's why we need to put it here in the stack. Now it's calling its left. So what's 2 dot left is 1. So now 2 dot left, which is 1, is being called. We didn't go to the next line. Okay, the print line we didn't touch. When we were just here, it's root dot left, this line, we hit the call again to call the same function again. So we call now 1. Now again, my value is 1. So we'll check whether it's none. No. So we are again hitting root dot left. So what we'll do, what was executing? 1 was executing, right? So it isn't complete. Even 2 is not complete yet. 1 is not complete yet, right? And that's why we put in the stack, because we need to complete them later, right? Until we hit the base case. When we hit the base case, then we will come back to that. Now it's time for the base case. Why? Because now after, when 1 was executing, when you hit this line again, root dot left, then you are calling the same function again, but this time our input to the function will be none, right? Because 1 dot left is none, right? So what will happen is that it will also be inside the stack. It will be none, correct? Because we are executing that now. And we'll check now the base condition, and it is true this time. So what will happen is that we will return. And where we will return? We always return the place from where we were called. And this none was called from 1, which is the left call of none. And we know that we didn't go to any steps beyond this. So we know that we will return here. And since we have returned, what we have to do? We have to remove this. Let me have partial strokes. So as we are done, we have removed this. And now our function call is here at this node 1. And in terms of line, we are here. And now since we have returned, we will go back to the next line, correct? So what will be printed? What's the root right now? It's 1, and it will be right. 1 is up. 1 is still up. Now again we are hitting the same function in order, but this time to the right side. And what's the root right now? It's 1. What's its right side? It's none. So again we will have in order function with none, and we know that it's hitting the base case. So we will again return where, from where it is being called, and we know that this none is the right side call. So we will return to the call where it's root dot right. And since we have returned, what we have to do every time, we have to remove it from the stack. Now we will, since we have returned, we can go to the next line. And what's the root value? It's still 1. So what we will write? 1 is down. So 1 was up and 1 was down. Both calls of 1 are done, and that's why I wrote this up and down. Until it's up and it's not down any node, then we can conclude that we have to finish its right side. Okay, so only one side is finished of that particular node and one side is still remaining if the down is still not visited for that node. But here for 1 we have visited both the nodes, and we know that we have visited both left side and right side of none, right? Of 1, sorry, both are none. So both the calls are done. So we are done with this in order 1 function. So we can also remove that now. So this will be also removed from the stack. Okay. And where we will, since the function is complete, we'll again return to where, from where the function was called. Since both the calls are done, we delete, and from where the function was called from, it was a left call of 2. So we will be here where we are writing in order root dot left, correct? Now left side of this root is done. Okay, correct? So left part is done. We have returned here. Since we have finished, we can go here and write what is up now. 2 is up. So left part of 2 is done, but still it's not down yet. It's just the left part is done. Now we will call again root dot right. And what's root dot right? 2 dot right is 3. So again, in order 3 will be called. This is the node. And since in order 3 is called, we will again check is whether it's none. No, it's not none, it's 3. So we will again go to root dot left. So again, root dot left is called, and we know that 3 dot left is none. So of course we'll hit the base case, but we have to write it that it's in the stack. Now we are hitting the base case, right? This is the none. So this is hitting the base case. So we'll again return here. Why? Because this was the left call, and that's why we'll return to the left. And since we hit the return statement, we will delete this. And again, our control will be back to the node 3, and we will go further. And by going further, what we have to print? Root dot where. And what is root right now? It's 3. So we will say 3 is up. Now we go to root dot right, which is 3 dot right, which is also none. So again, the function will be 3 dot none, 3 in order of none, and we will hit the base case. And where will we return? We will return from where it was called. Where it was called? It was the right call. You can see none. This none is on the right side of 3. So we will return to this right call. And of course, when we are returning, we will delete it. And now we'll move to the next line because we have returned. So next line will be root dot well 3, and 3 is down. So now I think it will be clear why I have written this up and down. So you can see one is, both the calls of 1 are done, 2 is still not done, and both the calls of 3 are done. Okay, and now we'll return because both the calls of 3 are done and the function is finished. It will be popped out from the stack. And where will be our flow returning? Since 3 was the right call of 2, you can see it was the right call of 2. Okay, so we will return back to the place from where it was called, which is this right call. And now we can go further, I mean. And now we know that what's the root value? It's 2. So what will print? 2 and is down. So you can see now 2 was up and down. Both the calls of 2 are also done, and we are done. Finished. We are done with this entire tree. The same thing you can do for this thing, and that will be your homework. That go root dot left, and then left, and then it will hit here and then hit here. Okay, so that's how recursive flow works. And now we will use this recursive flow, okay, to write the Leetcode function that we have. Okay, so let's go there. It's pretty easy now. So what we have to do is that, mind you, I have used the recursion with none type. Okay, so I'll use the same, that it's a none type. So what I'll do, I'll just write one variable, sorry, which is valid, and initially it will be true, and in the recursion we will make it to false. Okay, and if then we'll say we'll return this. Okay, and firstly, let's not do this, but what we can do is firstly let's write a function which is self dot in order. We are writing root, and we will define that in order function. Now I'm writing our in order function. In order will be having the same arguments. I'm not currently writing a function to solve this question, but I'm just writing what we discussed. So it's a none type function, and what we have to do is the base case first, and then the logic case. And what was the logic case? Is that we have to call the same function again. Oops, ORDER, but this time on the root dot left. and we will just print root.well and is up, and similarly I'll just copy paste it. Left side is done. Now the right side and is down. In the base case, as we know, if my root is none, or you can write root equals none, then we'll just return. Okay, right now it's not needed, we are not solving this problem, so let's just not focus on that. Let's just execute this. Okay, and let's see what we are getting as a prints. We are not concerned about output. It might show accepted or something. Yeah, it shows wrong, but we don't care. Okay, what we have to do is we have to check whether what we did on the whiteboard, are we getting the same prints? One up, one down, two is up, then three up, and then two down. Are we getting the same? Yes, one up, one down, two is up, then three is up, three is down. So this is to understand the flow of recursion, that how the recursive flow works, correct? And you can see it's working fine. Okay, now let's try to take the example. Let's modify this as our test case. I hope I can modify test case. No, I think I can. Why I am not able to edit it? Let's try to submit. It will be wrong, of course, but can we use some? Now I can. Perfect. So let's write the tree, the big tree. Okay, that we have. And what's that? We have 100, then 50, 150. So first it will be 100, then 50, 150. You can see real time it's being done here. Then 25, 75, 120, and 180. 25, 75, 120, 180, 10, 30, 60, 80, 10, 30, 60, 80, 110, 130, 160, and 200. Perfect. You can see the same tree. You can usually see here as well. So that's what my new test case is. And now if we run this, let's see what we get. Oops. Yeah, a lot of things. So this is what you have to do, that how we are starting this as a tree. You can see this tree, that firstly, as we can see, 10 will go all the way to left, 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 and will come to 10. Then first 10 will be up. We'll check both of them, left and right side of 10. They are none, right? Then 10 will be down when the both calls are done, and we will go to 25. Since left call is done, 25 will be just up, but it won't be down until the 30 is being done. So 30 will be up first, right? And then 30 will be down, both the calls will be done, and then we'll move back to 25 again. And that's why after 30, 25 is down. And then since the entire left half is done, we will move to 50. So this is like in order traversal that you will get. That's why I printed this. So that's how recursion works. So I want you to do this on hand by hand and just verify that you are getting the same order. You can take a little bit less level of one level less of this binary tree, little bit lesser, you can say smaller binary tree, and then continue so that it's not that time consuming. But I highly recommend this because this will be helping you to understand the flow of recursion. And now since we are understanding the flow of recursion, now what we have to do simple is that all these values, you can see if I remove, what we have to check, we have to check 10, 25, 30, 50, all these are in ascending order, right? Or the non-decreasing order. And since we know that we are traversing that way, what we have to do, we have to just check the previous one. That is, first will be 10 and then it will be 25. So we have to just check whether 25 is less than 10. Then when we come to 30, what we have to check, we have to just check it with its previous. Previous is 25 here. So we have to just check whether 30 is greater than 25 or not. Then after 30, our flow goes to 50. So we have to just check whether 50 is greater than 30 or not, and so on. Correct? So that will be, this is not needed now. Okay, we'll just have the root dot value. So it will be, let me just write that. What we are doing, we are going to left, we are processing the root, and then we are going to right. Correct? So it's like in order traversal. Now if I'll print this, then what you can see is we are getting this in a ascending order, you can see. So in order to do this question, what you have to do, we have to just simply write or check whether my previous value is greater than the next value or not. Okay, for example, we are at this node and you have to just check it with 10. Okay, so what we will do, we will simply write one variable which will track our previous. So for the starting, right, our previous will be none, because for 10, right, first will be 10. So for 10 there is nothing to compare. So we'll write our previous as none for the starting one. Now I will take, this is my output function, is valid BST or not. By default it will be true. Okay, so in our recursion we will set it to false with using this condition by just comparing the previous. If that doesn't happen, then we know that we didn't find the breach and we will return it. So what we will return, we will return our self.isValid. So by default is true. We will find something in the recursion, okay, by just comparing it with the previous value, and if we find, then we'll make this to false and then it will be false. Okay, because this is self.invalid. So what we have to do, base case will remain the same, nothing will change, right? Just what we have to write is, while processing the root, while printing the root, we have to just check if my previous dot well, so if my previous value is greater than or even equals to, because equals to is also not allowed, the root dot well. Okay, what's the current root value, which is what we are printing, that's why, and the previous value. For first, previous will be none. Let's just write it, and what we will do, we will just simply write self dot is valid as false. Correct? So what will happen is, firstly the previous is none, so this will give an error that none dot value doesn't exist. What we will compare with, right? So for first we don't need comparison, and that's why we will write one more condition, that we have to just check this condition only if my previous is not none. End. So if both this condition are true, then we will say it's false, or else it's true. And let's try to run this. Oops, what is happening? Wait. For this, we got true. Didn't, it was not able to find the breach somehow. Wait, what happened? We have to check root dot left. Oh yeah, we forgot to. Every time we have to update the previous, right? So for example, I forgot to do one thing, that when we are at 30, then our previous should be 25. So every time my previous should be updated to root. Okay, you can see it works for all the test cases. And I'm just, you can remove this print so that the standard output will be removed. Okay, so what we are doing is that we are just checking every time that whether my previous is less than the root. If it's not, previous is greater than my current root value, and that's why I have printed this root value. That, and every time I'm updating this previous, okay, to the current root. So when we are moving to the next route, that is 25, our previous will be 10. When we are at 30, our previous will be 25. If anywhere this condition is not satisfied, that is our previous is greater, right, then we will simply say it's false, correct? And this is how this function works. Now this is recursion is a really vast topic. So what I'll do is that let's say let's breach somewhere. Okay. I have to figure out how to edit the test cases. I have to figure out that it's working fine. But I have to figure out how it allows to edit the test cases. Oops. Case 1, test case 2. Yeah, here. If you go to test case and then do here, you can edit. Let's breathe somewhere. So let's breathe here. Let's exchange 20 instead of 25. Let's have 35. Okay. Then it will be a problem, correct? Because this is not allowed. Now let's run. See, output is false and expected is also false. But one thing is, let me visualize. We are breaching here, right? Then we should stop. But we are not stopping. We are going all the way to 200. Can we do something for that? And if you think, what we can do is, what if I can return? And let's try to run. See, it's just going until 200 again. Even I am returning. Why is this happening? So it is not bothered if I'm writing a return or if I'm not writing a return. Why is it so? Because return will return to the place from where the function is called. Okay, so whenever this breach will happen, it will return back to the same line of the code from where it was called. Okay, but it doesn't mean it will stop the recursion. Recursion will still continue. Okay, and for this purpose, we have to do something called as conditional recursion. And I think the video is a lot bigger. So let's move to the conditional recursion as a separate video in the very next chapter. So the hint is that what if we find a breach? What if we don't call the right road? Okay, so if we find the breach here as well, here only, then what we'll do, we'll simply don't call the other recursion, right? And that's what it's called, conditional recursion. So we'll see that. As of now, stay tuned and please try run this, the entire tree. Okay, really useful. Thank you.